Okay, late in the day, so I guess we will round it off. I don't think I will use the full hour, but this talk is going to be on IoT. I mean, most of the people on this conference, I think, are more software developers, but I actually come from a hardware company, which actually makes stuff. I work for a device maker that feed the end nodes of the Internet of Things. So that's what we're going to talk about in their security. Actually, I used to hack this very fancy equipment called quantum cryptography systems. Back in the days, there are some tens of them. It was claimed used by Pentagon, and I got access through some armies. But then I figured it was better to secure some billion devices in the Internet of Things. So before we start talking about the security in IoT, I want to talk a little bit about why are we doing this. Like, to me, often in security, the Internet of Things is kind of the laughing stock of security, where there is one headline after another how insecure this is and how dangerous this is to the world, and then most security companies laugh at this and don't want to be a part of it. So this is old numbers. It's like, actually, I was at a different conference earlier today, and they talked about 1 trillion devices, I guess, to get to another level. But you heard different numbers. This says 8 billion devices by 2020, which is 2 years out. So I kept that in there. But basically, the gist of it is it's going to be a huge amount of devices that are connected to the internet. And so you can ask, how do you get to 8 billion devices? I guess this application never ceases to amaze me in the sense that someone actually went off and made a Bluetooth-connected fidget spinner that I guess contribute a lot in numbers. As a security researcher, I also think about the security of this thing in the sense of the Trojan horse could have a whole new facet with this one. But anyways, to me, it's fascinating that someone can actually... Hardware is so accessible these days that someone with a minimum of knowledge can actually go make a connected fidget spinner. But I don't think that's why we're connecting all these devices. I think to exemplify that is like, this is a McKinsey report stating the value of the IoT from $4 to $11 trillion. And it's like broken down on different like human, factories, cities, etc. It's like how much value. And then the question is, what does that mean, right? Why are we doing it? What does it mean, $4 trillion? Who gets that money? So let's do some napkin math to kind of talk about what this means. If you assume that the total value is $4 trillion, so in the lower end, and then typically, historically, when you have this kind of value, 50% is salary costs. So if you produce something for $100, typically at the end of the supply chain, $50 went to salary, $50 went to capital. That's kind of on average. And if you say that the average salary is $10 per hour, and a worker is 2K hours, and then for the simplicity of it, let's say 8 billion people on the planet. What this means, if you unleash $10 trillion worth of value, is 200 billion salary hours. Or it's the same as 100 million man-years, which is kind of the entire workforce of the US. So one way to interpret this is that if you unleash $4 trillion of value, everyone in the US can retire and do nothing. Because now, and the interpretation of that is because you have now automated the water sprinkling, you have automated the stores, you have automated all of these things, the cars, all of this. There's nothing left to do. You can live automatic. Of course, that's not how it will play out, but for the mental image of it, 25 hours per year per human, and 1/2 hour per week per human. So if we unleash $4 trillion worth of value from the IoT, it means that every one of us get 1/2 hour per week extra that we can use for something else because we automated something, some repetitive task that we didn't want to do. Like mowing the lawn, we have a robot that does that. Or vacuuming, we have a vacuuming robot who does that and is connected to the net, and so forth. And effectively, I find this kind of amusing because what this means is this is going to be very unevenly distributed across the globe. So it's not like every person in Asia is going to get, and Africa is going to get 1/2 hour per week extra because something is automated. And we in Norway, and industrial and modern societies are going to get way more of this as a fraction. And this is what is talked about when everyone talks about what should people work with when everything has become automatic, like when machines have taken all the jobs. Well, this is what actually happens. So what we have done is we have taken all these low-hanging, repetitive jobs that no one wants. But when you do that at the scale of the Internet of Things, that means that we get a lot of spare time. And not everyone can work the way they used to. So this is, and I think also this is why this is going to happen. It's like a mega force that's impossible to stop, basically. Even though a lot of people say we shouldn't connect all these devices, given the gains of it, we are going to keep doing it. So IoT security, the IoT security of guns. Since we're in Norway, I want to highlight a few hackers. This is a female hacker that hacked from Norway. Got a lot of media attention when they hacked this gun. And basically what it means is there is this smart rifle with a Linux processor and an aiming mechanism. So you can aim at what you want to shoot, and then you press a small button, but it doesn't fire the gun. And then afterwards, you fire the trigger, and when the gun is in the right position, the computer will fire at the right instant to make sure you hit your target. And the reason why this is effective is that a lot of people, they will when they fire, they will skew the gun and actually miss. But when the gun fires by itself, you're not prepared for it. So it will actually be correctly positioned. It turned out that it also has a streaming capability where you can you can send your favorite hunting video to your best friend. And they were able to find a vulnerability in that Wi-Fi interface and skew the parameters of the gun so that when you shoot here on the left, you actually shoot on the right. They could not remotely fire the gun, but they could skew the parameters. So this is one example of where this is becoming life and death. Another one is, this is also a Norwegian female security researcher, Internet in the Heart. So she got a pacemaker and figured out she wanted to understand if there was any extra interfaces here. And there was, and basically, for a lot of pacemakers, it turns out it's insecure in the sense that someone with that are within radio range of the pacemaker can modify its settings and potentially even lethal. One of the way the medical industry is combating this, by the way, is by use of a huge magnet that needs to be on top of the medical device to put it in RF mode. But this is becoming pretty serious. And I have another example that is a little bit more interesting in the moment. But why doesn't classical cybersecurity work anymore? Because I mean, it's like we have been facing these kind of threats for 20, 30 years. And basically, this is kind of the picture, the pre-Internet of Things picture. How I see it, you have like a few devices, like an access point, a computer, and a phone. And there is like a very small number of devices that you actually have to secure. And if you have something like smoke alarms that talk to each other, it's a proprietary network, and they are usually just an isolated network. And on the server side, it's very easy, because on the server side, you put it in a mountain vault somewhere, and then you put thick doors and a lot of physical security around that, so people don't get a hold of it. But in an Internet of Things setting, this is what it starts to look like. All of these devices, like light bulbs, wash machine, TV, all of these can now communicate on many different protocols. So the number of devices you have to secure is huge, and they can start contaminating each other. So talking from a security point of view, the attack surface just exploded. compared to the previous setting. And accessibility to hardware has changed the game a lot. Because many of these IoT devices are sold as services, not as devices. What I mean by that is like my laptop, I can break open my laptop. Dell doesn't care. They don't have any secrets in there, so I can just break it open and do whatever I want. It doesn't matter to Dell. I have a Garmin smartwatch. Garmin cares, because their IP is in the program that's actually running on the smartwatch. If I can use that to get access to other smartwatches or health data, etc., that's a different story. So the big difference on the Dell, I can install whatever I want. On the Garmin, I should not be able to install whatever I want. The software on my smartwatch is owned by Garmin. So the accessibility to hardware, that you're actually hacking physical, something you can hold in your hand and not a server in a vault, puts completely different requirements on what you're trying to do. And limited processing power in the end nodes is also one big difference. Like earlier, you can do endpoint security on computers, you can do antivirus, you can do a lot of this, take a big chunk of the processing power of the end node, of the device, but you cannot do that in IoT. So then, but getting to another application, what kind of security requirements do you need for a light bulb? Or is a light bulb critical infrastructure? Maybe. Perhaps the right question to ask, I mean, is a light bulb critical infrastructure? Most likely not. Is our light bulbs critical infrastructure? Potentially. So this is kind of one of the aspects that IoT vendors are facing, that you have this scale of the IoT, and parts of the reason why the security is what it is, because you have the scale, so single devices are not critical, and that's the way we tend to think about it. Like, no one cares about the light bulb in my living room, so no one are probably going to hack it. But the problem arises if someone can get a hold of 1 billion light bulbs, or some billion light bulbs. That's when it goes from completely, it doesn't really matter, to very critical. And the other aspect is that security and privacy is a balancing act, especially in the Internet of Things. I mean, it has been for some time in traditional IT security as well. You can think about the password policy. That's kind of a balancing act. If you make people change too often, they start writing it down on post-its under the keyboard, or just cycling a number. That's kind of another example of a balancing act. Or if you enforce too many characters, etc., it's a game. In security or IoT is a little bit different, and typically one of the challenges here is like there is this joke, how many engineers do you need to install a light bulb? And that's actually moving from a joke to reality. These connected light bulbs, you typically need a lot of engineers, actually. It's typically you need a network or a manager, and you need a building manager, and you need someone to wipe the all connected light bulb. So in the US, there are actually companies that are starting to do this as a service. And on average, they connecting like commercial connected light bulbs takes about 20 minutes of engineering time. So that's also why, in many instances, companies will lean back on security to make it easier to install. Like one device that we made the chip for is this IKEA trådfri, if you have seen that. That's a light bulb with a remote, very good value proposition. When you install that, it's far from perfect security, but it's really, really, really easy to install. So my mother can actually do it. And that's kind of a trade-off they had to make in order to make this a viable product. But one of the challenges that in this IoT is also who's the adversary and why do they attack? And this is a little bit different or I would say you have the same classes of adversaries, but it's a little bit different how they attack. Because typically you have this hobbyist script kiddie and advanced hackers, security researchers, and then nation states. And in a hardware setting, when a nation state wants in, a nation state gets in. There is no debate around that. There is nothing you can do, basically. Because once they have the device in their hand, they can crack it open and reverse engineer it to a point where it's infeasible to have commercial consumer IoT devices that are secure against nation states. There is security researchers you have to try to protect against. And the reason for that is that they actually hack stuff and go to Black Hat and conferences and show that your stuff is insecure, and you get into an issue with your customer base. But what also happens, so first, if you want to secure an IoT device, you have to choose who I'm trying to secure against, and then you have to try to choose your adversary, and then make decisions based on that. And by the way, one of the differences between traditional software and IoT is also that in traditional software, or software as a service in the cloud, you can always patch. You can always take down the service and patch it. But you cannot do that anymore. Once you have sold hardware, it's out in the field, it's a completely different situation. Or with all the e-meters that are sold in Norway these days, or not sold, you're enforced to take it. It's not any longer necessary. And what this talk is about is how you need to have a strategy for updating them, because you cannot necessarily patch if you don't have a strategy behind it. But what also happens is that there is a commoditization going on hacker tools for this kind of devices, and especially in the physical space. I mean, the cyber analogy of that would be that the Spectre and Meltdown pops up, and then a script is unleashed on GitHub, or the Mirai botnet attacks, and the script is on GitHub, and suddenly the script kiddie can do it. He couldn't do it before, but now he can do it. But it also happens around physical security. So I don't know, are you familiar with differential power analysis? Some nodding, some not. So differential power analysis is when I take this device and I want to get cryptographic keys out of it. What I can do is that I can look at the power consumption or the electromagnetic radiation from the device. I can just put the antenna on top of it. And then I run cryptographic operations. And then if I have a sensitive antenna and enough post-processing, I can get the keys that are inside of the device. And in a software as a service setting or a cloud setting, this is not a problem, because you have guards and thick metal doors and bars and whatever at your server room. But this is a problem when everyone has the device in their hands. And this used to be kind of a security, it used to be a, who knows, nation-state attack before the mid-90s. And then it became a security researcher class of attack. There was a company called Cryptographic Research that unleashed equipment to do this that everyone could go and buy for around $100,000. It was still prohibitive. It's not like you have students at universities buying that and doing it, but at least now it was in the public domain. That still meant that typically companies didn't, when you make a light bulb, you typically don't have to care about this at this point still. But then someone made something called Chip Whisperer and put it on Kickstarter for $300. So suddenly this went from being like a military-grade attack vector to becoming like a hobbyist attack vector. And I bet that if you buy a military system from, say, early 90s, you can probably now hack it using $300 worth of equipment. Because this just wasn't known at the time when this military equipment was made. So if you look at the differential power analysis today, this is Chip Whisperer. It's actually $250 now. They probably got a little bit up in volume. And this is becoming so usual that it's actually one of the primary attack vectors when hackers go after IoT devices today. So this on the right is a publication called IoT Goes Nuclear, creating a Zigbee chain reaction. And this was a couple of years ago. Someone hacked a smart light bulb, this Philips Hue, if you're familiar with that, and made a demonstrator where they could make a worm that would infect bulb to bulb to bulb to bulb. And since this is a proprietary network, you can't stop it using ordinary methods, because it will spread from house to house to house and not go via any ISPs or internet providers. And to do this, they use DPA to get basically the secure bootloading keys out of the device. Another example is EMI injection attacks. So what you do then is that you basically put a big magnet on top of the device, and you fire a big magnetic pulse with the purpose of making the device misbehave. Skip a password check or go into some strange branch in the code or do something stupid so that you can get access to it or get access to keys. And this was the same story. At some point, there was a company called Risecure that started selling these probes and kind of publicly doing this in the public domain. And now it's a $350 workstation. So EMI today looks like this. You buy a 3D printer and you make this circuit board that's on GitHub. And then you can start blasting away. Typically, you have to. The reason why you use a 3D printer is it's a very cheap way of getting a micro positioner. So the first thing you do when you do these EMI attacks is that you scan the chip over the chip, position the probe, so you find where you have to put the probe in order to successfully disturb the processor into doing what you want. So one of the learnings from this, the fact that there is this commoditization going on in the hacker tools, is that when you make an IoT device, what I have here is level of security and adversary strength on the y-axis and time on the x-axis. And then when you make some kind of IoT project today, you have a choice of security level and the adversary strength. And the way to interpret this is that if the choice of security level is over the adversary strength, you're good, and if the opposite is happening, you're not good. And what happens is that the adversary strengthens over the lifetime of the device. There are always new novel attacks. Sometimes it's incremental, like bigger access to processing power, cheaper or bigger access to memory. It's kind of a predictable process following Moore's law. Or sometimes you have these steps where a completely new attack is found that no one thought about up front. And the only way to battle this is to upgrade the security during the life cycle. That's the only way you can do this. And this is actually surprisingly expensive to have the infrastructure to do this. And most companies that put stuff on the internet today, things, they don't think about this up front. But if you're going to do it, you have heard this talk, so you're definitely going to think about this up front. And sometimes you cannot patch the attack. This is the big difference between software and hardware. So if you don't have the necessary hardware requirements today, you simply cannot patch your way through this. And so there is one different solution to this, which is kind of elegant, which is kind of the phone story. And that is just make sure you make the lifetime of the device really short. So make everyone throw away their phones every 2 years. It's actually a very effective way of managing the security of the phones. Because then you can upgrade the hardware every 2 years, and you know it's not a big issue. But what if you sell a wash machine and put it on the internet? Then you have to start asking yourself, who or what is the adversary of 2035? And there are companies asking themselves this, that want to put Internet of Things devices on the net. And again, the only way you can handle this is impossible to predict. I think it's probably machine learning or some AI. It's not necessarily even human. But the only way you can handle this would be to have a strategy around it. And it's not. And the root of that strategy is that you need upgradability. You need to be able to update the security during the lifetime of the device. And there are a couple of things you need. One is secure boot. So secure boot in this context is a bootloader that will only accept images that are authentically signed from the vendor. Meaning that my Garmin device only accepts firmware that's coming or software that's coming from Garmin and not from anyone else. And it has to use asymmetric cryptography, meaning that there are only public keys in the device because protecting a key inside a physical device is really, really, really hard, and you cannot rely on it at scale. And then typically a lot of companies want to have confidentiality. They want to encrypt the image as well. And there are two reasons. One is protecting their IP, because most vendors like Garmin will be paranoid about a factory in China making counterfeit watches. And the other thing is it makes it difficult to find loopholes in the code. And then on deploying upgrades, you need a strategy for that as well. And one of them is memory requirements. How much overhead do you need in the device? What capabilities do you need in the device today? Because you need some kind of budget. And one of the challenges with software development is if you have memory on the device, the application will just scale to use all the memory. So you have to have a strategy of how you retain some overhead the day you actually need it. How is always a question. Is it directly connected to the internet? Does it go via gateway? Does it go? How is the actual connection happening? And is it forced? Meaning, will it update itself or will it ask? My phone keeps asking me if I want to update it, but perhaps that's not the right strategy for a light bulb or for some of these cases if you want to be responsive. After this VPA2 crack was discovered, some of the access point vendors actually just updated the customers' access points without asking. They just did it because they thought that was the right thing to do. And then who? You need some kind of system to make sure that not anyone in the organization can push updates. So it's a question of how is the authorization enforced as well. Typically with an N out of M scheme it is something that we recommend. So 2 or 3 people need to meet up to sign an update. So for a final discussion, I'm going to discuss a little bit, because so this is well known. We know how to do this. It doesn't require research or big inventions. The technology is there. But still, we don't see the adoption we perhaps should have. And one of the challenges is this. So it turns out this is kind of a research study. It's very small, but I can point to it. So these blue dots is what risk do you accept in a device or a solution. And the top of this curve means that you don't accept any risk. It says the top one, 31%, to avoid break-ins at any cost. And then the green bubbles is how much are you willing to pay for security? And this is directly applicable to a light bulb, as I will get to in a minute. And then what premium are you willing to pay? And then 42% says nothing. So you want to prevent break-ins at any cost, and you don't want to pay anything for it. And that's a little bit how a consumer thinks as well. It comes to this shelf, and he's not going to think about is this secure or not. He will just expect that if it's connected, it's completely secure, and then he will take the cheapest one. That's how it works. And this does not incentivize light bulb manufacturers to do a good job on security, or IoT vendors to do a good job on security. It incentivizes them to get fast to market, basically. So I think regulation is the right path around that, and there has been many proposals lately for that. One is this kind of labeling, like what we have in wash machines and electrical appliances, with different security levels, A, B, C, D, etc. I really don't believe in that at all. And the reason is that what I just mentioned, like to the public, to most people, security is binary. It's either secure or not. But as a security researcher, there's a lot of context that's missing in that kind of statement. It's like, my front door is secure against someone with a lockpick, but it's not secure against someone with a bulldozer. So you have to kind of specify the context, specify the adversary. And this kind of labeling, I think the public is not going to understand. They're thinking binary, so if they buy A++, what does it mean when it gets hacked? Are you going to say, hey, I paid 10 kroners or $1 extra for A++ and I still got hacked? It's kind of, it doesn't make sense. In the US, there has been this big bill called the Internet of Things Security Improvement Act. And basically what they're trying to do here is to have a National Institute of Technology mandate minimum security requirements for all the devices that go into federal buildings. So they're trying to use the purchasing power of federal buildings to raise the security level of these devices. It's also a good, or it's a better way. The challenge with this is who is going to test all these devices and mandate a certain level. So I'm actually a big fan of GDPR. It's not perfect, but what I like about it is, in particular, it states responsibility. Who is responsible if data gets lost, and what's the fine for it? And what I like about this is that it hands out the responsibility and actually incentivizes vendors to do a good job without telling them what you need to do. They're telling just what you need to avoid. And then it's up to the vendor to kind of raise the bar for that. So I think GDPR is going to do some for IoT, but I really also believe that regulation has to be, will arise at some point. Hopefully not after a huge breach, and then the regulation is done in panic, but rather as a strategic process. So with that, I'm going to summarize. Security is not binary, which complicates a lot of things, and it's important to consider the adversary of the future when you make IoT devices. And therefore, it's impossible to predict the adversary of the future, so the only way you can do that is make sure you have upgradable security in your devices. Thank you very much. Questions? Yes?
Suppose you have some kind of trusted zones available in ARMs in IoT devices. Would it solve problems with security?
Yes, so the question is, if you have trust zone or software isolation, as I think of it, in
More isolation, like security features and keys, probably also a certain specific part of the processor.
Yes. So the question is, if you have isolation, trust zone, and some of these features in the processors, will that help? And yes, I mean, security is typically a game of layers, meaning so it depends a little bit about what attack vector you look at, because it will help against some and not against some. Like if you're doing differential power analysis, it doesn't help if your crypto is running in the trusted mode or non-trusted mode because it's leaky. It might be leaking the same way anyways. That's where a hardware engine that's robust against this kind of attack helps. If you're looking into, say, buffer overflow attacks or kind of vulnerabilities in a network stack, it helps a lot if that network stack is isolated, such that you don't get system-wide privileges if you have a breach in that. So it helps, but it has to be used carefully and in conjunction with other countermeasures. Other questions?
Is this only theory, or do you know any security product that can be upgraded? Have you been working with some technology that actually uses upgradable security?
So the question is this only theory, or have I been working with companies that actually do this, use this strategy? And yes, there are definitely companies out there that use this strategy and go to great length to do it, because they acknowledge it's the only way that they can remain secure. And it's especially, I mean, again, some of these devices have 20 years of lifetime, which is unheard of in a laptop or a phone setting, but it's and even in a smartwatch, in the consumer space mostly, but in the industrial space, that's more the rule than the exception. Okay, thank you very much.